Well, good afternoon, everybody, and welcome to the Thursday, October 10, 2019 session in our series on edge computing, where we're trying to explore whether the U.S. and Asia are going to go in different directions. I'm Richard Dasher. I direct the U.S.-Asia Technology Management Center. We produce this series. I also want to recognize the member companies in our Industry Affiliates program because they are our primary source of support. That's how we get along, including salaries and everything else that we do. Thanks to their support, we'll have some refreshments outside after the session is over, and we hope that you will come and meet. Some of the people from our companies are here today, and you can see the list of who's involved in a chart outside. So we started off, I gave an overview a couple of weeks ago, and last week, Professor Paulraj talked about 5G networks. So the next kind of major enabling technology for edge computing is really AI processing chips, AI or chips, computer chips that accelerate AI processing and also reduce power and so on and so forth. We have somebody I'm absolutely delighted to introduce to speak to us on this topic, exactly the right person again. Gary Brown was one of the very first research assistants I worked with at Stanford before many of you were born. And Gary was an master's candidate in electrical engineering at the time, and we were working on reading Japanese technical literature in Japanese and providing reports on that to the Silicon Valley community. And some of what we did led to us being the first place outside Japan that Professor Shuji Nakamura presented his work on blue LEDs. He hadn't even developed the laser at that point. So I'm really happy that I can ask Gary to come back and speak to us. After graduating, he became a field engineer. He worked with Dolby Labs. Then he did engineering sales support for several startup companies, moving up to bigger and bigger size startups until he got to Tensilica. And then from Tensilica, he went to a company called MoviDus, which was one of the prime movers startup companies in chip acceleration. And a couple of years ago, Intel bought out MoviDus. So now Gary is the director of AI marketing for the IoT group inside Intel. And he also has extensive international experience. I'm glad you could be in country this time in order to talk to us. Gary, thanks so much for coming.
A pleasure, Dr. Dasher. Richard. It's great to be on the Stanford campus. Back when I was a master's student, I got to hear a talk by Gordon Moore. Many of you have heard of Gordon Moore. At least you've heard of Moore's Law. That was named after Gordon Moore. And he gave a brilliant speech here as a part of the Hot Chips Microprocessor Symposium. The only thing I'll say about it is the reason why it was so brilliant, it had nothing to do with Intel. It had to do with the industry and the challenges that the industry is going through and the promise of being able to develop faster and faster microprocessors, which everybody in this industry was focused on. And what a brilliant talk to be able to speak to the industry about what we all have to do together, rather than to focus on what your company is doing. So many times when I'm speaking, I like to try to educate about what's going on in the industry and take the focus a little bit away from my company, but focus on things that everyone has to do, and maybe provide a few examples along the way of what we're doing at our company to be more of an education, because I mean, after all, this is a university. But I wanted you to think for a second, have you ever walked along the street, I've done this before, and closed your eyes and tried to remember where things were on the street? And imagine what it would be like if you were blind. There are many, many blind people. But if you do that yourself, you'll realize very quickly that your sense of touch and your sense of hearing really pale in comparison to your sense of vision. And people say that your visual capabilities take about 30% of your brain's cortex, where maybe hearing is only 8%. Feel and touch only 3%. So the primary use of your brain is really vision. And if you look at the extension of your brain cells that capture light and are sensitive to light in your eyes, and then trace millions of paths through back to your occipital lobe, you find out lots of amazing things about what the brain can do with vision. And neuroscientists, of course, have been studying that for many decades. And then a little while back, maybe 30, 40 years ago, computer scientists thought, what if we create a model of a neuron? What if we put numbers and calculate based on what the neuroscientists are doing and kind of mimic that and have computer algorithms that can mimic the human brain? Thus, AI was born. And AI was born quite a long time ago. But it wasn't until recently that we have enough computing power to do AI. So it's an exciting topic. There are new chip technologies for AI that I want to be talking about today. But I'd like to step back and first tell you why this is so important and why it's interesting. Also, how it works and how people are starting to examine these kinds of problems. And then maybe finally what some examples are. And then you'll be experts at the end, and you'll be able to go lecture everyone you know about AI in edge computing. So let's get started. Some disclaimers about the numbers that you'll see in the talk here today. So Professor Dasher gave a brief introduction. So when I'm not playing jazz, what I like to do is work on microprocessors. And as he said, I have some international experience. I started out working for a company in Osaka called Panasonic. Matsushita at the time, they changed their name, and came to Stanford to work for the US Technology Management Center. But the processor technology always seemed really exciting to me. And in the year 2000, there was a really brilliant renaissance where people decided, you know what, we don't have to build the whole chip. We're going to buy from somebody who designs a piece of the chip. We'll license a piece of the chip, and we'll license another piece of the chip. And so suddenly the IP industry, intellectual property, in the context of semiconductors meant that a group of people, 2 people, can design a video codec in their basement, license it to IBM. That actually happened. And then I could be looking at the IBM chip and testing it and realizing, wait, this audio codec, something's wrong with it. And then the people at IBM say, well, we licensed it from a third party. So it was a really interesting thing that I saw when I was working at Dolby Laboratories, that a lot of the chips we were getting and testing and supporting, the pieces and parts of those chips were actually IP coming from other third parties. And so I thought, this is a brilliant way to design chips. I want to jump in and get into that. And I went to go work for Tensilica as an audio systems engineer. And the rest is history. But it wasn't long before I got into video processing. And of course, video is important. But eventually, vision became a very, very important problem. Because there's a lot of things you can get from video if you extract meaning from the video frames that are being captured. So something else I can say, MoviDus was a company that was pretty early on designing a chip that could actually do camera processing and some computer vision technology at the same time. And there were some other companies doing that as well. And nowadays, if you say computer vision, just about everyone seems to be working on computer vision technology. So let me step back a second and just define what edge computing is. Because I think looking at most of the speakers that are speaking in this series, there's a variety of definitions that you might want to look out for. So I thought I'd give you a little bit of a roadmap when you're talking about edge computing with your friends and family over the weekend. You can understand a little bit more. So we start at the network edge, where there are devices or things, and they're networked. So the key aspect of an edge device is that the fact that it's connected to a network. It could be called a connected device. They have sensors, they're getting information, and of course they could be doing some computing, but they also could be sending it into the data center. And it has to travel through sometimes an edge compute device. So here I brought an edge compute device. It's a very small industrial PC. These kinds of edge servers are used for edge computing. And you can see it's very small. It's low power, it's cheap, it can fit inside a small retail store. You don't necessarily have to send the camera data into the cloud to get processed when you can do computing in the edge. So we'll talk more about edge computing, of course. So you're aggregating the data from the sensors, you're doing some computing, and then it's connected to a network infrastructure. It could be wirelessly talking to a base station. Now the base station is interesting because if I were in 5G, or telecom, I would be saying the base station is the edge. And so from a telecom or 5G point of view, the telecom edge is, or the comms edge, is the base station. But from the IoT and devices and microprocessors point of view, the edge is really the network edge where all the sensors are and coming into these edge servers. So there's a lot of different terminology, but essentially it's mostly about where the sensors are capturing data. If you're doing the compute there, then you're doing edge computing. And then you have the data center. So many of you who maybe use an Alexa at home, you're talking actually to the data center, and then the data center is doing the compute and sending it back. And it seems fairly low latency. But actually, it's a very long latency. There's a lot of power being consumed. And so when you do computing at the edge, you get immediate results. You could have very low latency, low power, privacy. There's a lot of benefits to doing edge computing. And we'll go into a little bit more detail. But basically, lower cost and power is the whole goal. So let's move on. I like to see statistics about how much data we're generating at the edge. Because if you think of vehicles as edge devices, which they are, they have sensors. If you think of airplanes, if you think of edge cameras or smart city buildings, anywhere there's sensors and data coming in, we have billions of gigabytes of information, or zettabytes of data that's being generated by the year 2025. 100 zettabytes is quite a lot of data. And the problem today that businesses are finding is that if they don't take advantage of checking out that data and processing that data, then they're missing out on opportunities to make their businesses more efficient. Why is that important? Well, take, for example, a fast food company that wants to make its French fries very quickly. And maybe they don't want to waste oil, or they don't want to waste food, or to minimize waste, wouldn't it be great if you knew who was coming into the lot, when and how many people were coming into the lot, how many people were coming through the door, how many people were coming into line? And you could pretty much develop models as long as you can track those people to figure out how many French fries you should be preparing so that you're not making too much, you're not making too little. This kind of information that you're gathering at the edge through cameras can actually be used to reduce the cost of running your business if you're running a whole chain of thousands or tens of thousands of fast food restaurants. So it's a really serious problem for businesses. How can they cut costs and yet be efficient and yet serve people really quickly before the French fries go stale? So that's just one example. But it's really transforming the way we live and work in a lot of different ways. Edge computing is improving quality of life in smart home. Many of you may have smart devices operating your lights or various kinds of systems at home. In agriculture, in public safety, there are a lot of ways in which edge computing and gathering data in sensors, using that data wisely, can help with efficiency, with safety, with lowering cost. If you think about, we'll talk a little bit more about industrial machinery and industrial manufacturing, where finding a product defect is very important. You do not want product defects getting into your products. Today, it's with a lot of manual labor that you can find defects, maybe at a rate of, let's say, 70, 80%, depending on how complex the product is, if you're a human being. But now put in cameras, and then you can get up to 99% or higher accuracy in finding a product defect just by having a robotic arm quickly take pictures of the device. Now, is it replacing the human doing the manual labor? Maybe. But is it creating a lot more jobs to maintain the robot and maintain the cameras and maintain and watch the system? Yes. So it's not necessarily a robot taking over a job to do it more efficiently. It's creating some jobs as well. So there's an interesting angle to be looking at industrial manufacturing. Now let's click one more level below and see what kinds of things are taking advantage of edge computing in various kinds of applications. For industrial, I talked about machine vision over there. In smart cities, analyzing traffic, parking, license plate recognition is a very popular algorithm that you would implement. Some of you know LPR is license plate recognition. Emergency response, people counting for an ATM at the bank, or if you're walking into a bank, knowing how many people are walking in and out and using the ATM, reducing wait time by having some customer feedback or some maybe facial recognition at the ATM, not because it's going to be sending your face to the police, but it's because it's looking at your sentiment and giving you extra help, or maybe connecting you with someone live if you seem to be having trouble or you're looking like you're frustrated. So there's a lot of interesting AI algorithms that could be put to use in edge computing to improve your experience. And in transportation, of course, autonomous vehicles have tons of sensors, various kinds of modes, LiDAR, radar, vision sensing, to be able to take you along and analyze the world around you. So those are just some examples. Now, AI technology in general is growing very, very fast. If we look at some analysts that have estimated the growth of AI technology, we're talking about $50 billion here, down here where we are, and then growing in terms of hundreds of billions of dollars over the next few years. So we believe that it will create about $13 trillion of additional economic activity just in the next 10 or 11 years. So there's actually a lot of activity in many different industries going on with AI. And one question you may be asking is why? Why now? Why not 40 years ago when these kinds of models of human brains were invented? I think it's because the compute capacity that we have today in microprocessors that can fit in a very small box or in a small device or maybe even on your wrist or in a cell phone, there's a lot more compute capacity, and it's basically reached a point where some very basic and very high accuracy AI algorithms can be implemented in a very small, low-power microprocessor. So we've sort of reached a point where the computing capacity required for very accurate AI algorithms that are valuable in these kinds of businesses, you can now get for $5 or $10 and put in a small device. So how does AI work? I thought I would explain maybe in 1 or 2 slides what AI is all about so that you can all become PhDs very soon in the topic. So AI is actually the mimicking of a human brain, a very general kind of topic. But if you dig down into various aspects of AI, there's something called machine learning, a subset of AI, where a machine is actually iterating, and maybe there's some error in a robot trying to tie a shoelace, but it gets better and better as it tries to reduce the error, and so it's learning, or quote-unquote learning. So reducing error in a machine algorithm is machine learning. But more specifically, when you get to something called deep learning, that's where you hit the ability to do machine learning, but in a very regimented way with these kinds of model neurons and layers of these neurons that look something like this. So you do a lot of multiply and adds, and just maybe similar to the way a human brain's neuron will chemically either react or not react, you're basically passing through information from layer to layer in what's called a deep neural network. So deep learning is all about implementing a deep neural network. And these actually have been tuned, many people have been doing research on deep neural networks for decades. And so they're a very efficient way on a microprocessor in multiply and additions to be able to implement an algorithm that does machine learning. So there are 2 steps. The first is you train the algorithm. Now, if the algorithm is, let's say, recognizing an object, you might take photos or pictures digitized of objects, humans, bicycles, strawberries, many of these photos, pass them through and start to set the parameters of the neural network. So once the neural network parameters are set, you can then decide, okay, now I'm going to do what's called the inference step. We're actually going to deploy the neural network, and I'm going to put unknown images inside. Then when it sees an unknown images, with the parameters that have already been set in the training step, you would then be able to get out what classification. So the classification in this case might be bicycle. It might be incorrect, it might be correct. In some cases, you have to go retrain if you want to improve your accuracy. But improving your accuracy means you may need more layers of neurons. You may need higher accuracy neural network that uses, let's say, floating point, 32-bit floating point instead of 16-bit floating point, instead of 8-bit integer. So there are various ways and various kinds of magical ways in which people are training neural network algorithms to be able to do very useful kinds of things, like object tracking, like classification, like detection, and those kinds of things on images. So this is, I'm just focused right now on the imaging aspect of AI. So that's it, training and inference. When you're deploying or creating camera-based implementations, you would be performing inference. And many people will ask, what's the performance of the inference? How many inferences can you do in 1 second? How many inferences can you do in a watt of power? How many inferences can you do in this much cost and this much space? And so the inference performance is what people will ask when you're trying to deploy the product or the thing or the device or the server that's actually going to be out in the field. But in order to develop, the developers back in the lab will spend days or weeks or months actually training algorithms. This is where you need a lot of compute power. You need to be running many, many images through hundreds of millions of images, large data sets. And so this is why people buy very large data center grade CPUs, GPUs, FPGAs, all kinds of accelerators that are more suited for the data center, so that when I'm connected to the data center and I'm doing my training algorithm, it'll spend, maybe I'm only spending a week instead of 2 weeks. So there's the training, which is an offline kind of developer step, and then finally when you deploy the equipment, the inference. So hopefully that explained it. Now you're all experts. The key thing about AI, though, is traditionally you would write like a face recognition algorithm or a face tracking algorithm or object tracking algorithm, let's say for a point-and-shoot camera, and you would write the algorithm. It would be a human-engineered algorithm, and using a model of a face, and you would write it in C code, let's say, and it would be running in an embedded system. But these algorithms never really got too accurate. And the great thing about AI is that the accuracy of AI now can far surpass what a human-engineered algorithm could be. Now, there is a downside, though. It takes quite a lot of arithmetic. So if you have the microprocessor capability to be able to run as much arithmetic as you need to run the AI algorithm, then you can get amazing amount of accuracy. And here there's a little graph showing what deep learning has been able to do in terms of the error of detecting people or tracking people. It's now, the error is lower than a human set of eyes. So if you're watching video and you're being asked, where are the people in the video, today a computer running an AI algorithm can do it better than a human. So algorithms have become very, very accurate. Of course, the cost is in terms of the compute. So if you only have a very, like if a toy company wanted to create dolls that had some kind of image processing inside, I guarantee you it would be a human-engineered algorithm running in a very, very low amount of memory that's suitable for a toy. They wouldn't necessarily choose an AI algorithm, but if it's a camera in a car that needs to detect pedestrians and brake automatically, it wouldn't be a human-engineered algorithm. You would probably get much better results with an AI algorithm. But they would still have to develop it to get close to or maybe equal to 100% accuracy in the case of pedestrians. And so I'm still on the question of why. Why is this important? The opportunity in computing chip technologies, in edge computing chips, is actually an interesting kind of chart to look at. And I spent some time extracting some information that we had looked at Intel from various analysts and from our own analysts at Intel to come up with, I couldn't give you the numbers of this because some of it's internal information, but suffice it to say that over the next few years, over the next 5 years or so, there's going to be a growth in the endpoint device and edge computing, edge servers that do the inference. But there's also going to be a surge in training and the amount of silicon people are going to need to train the algorithms. The question is, which is growing faster? And as it ends up, what these analysts had found is that there's about a 25 to 30%, 35% growth in AI overall, but the growth is actually larger for both the endpoint and edge inference compared to in the data center. So the edge is growing really fast, and that's because, I think it's because in a lot of different industries, companies and businesses are making really good use of edge computing. And so there's a lot of silicon now in the last few years being shipped for agriculture and for visual retail and for medical imaging and all kinds of things. If you go for an X-ray, how many people still have doctors that maybe produce the film or actually go into a lab for the film? That still exists, and it's inexpensive. But some hospitals are now investing in the digital X-rays, and so you can do edge computing very quickly that way. So what are the benefits of edge computing, and what are the very strict requirements? Well, the requirements are a bit heinous because you need to have huge compute requirements if you're going to be running, let's say, a pedestrian detection in your car. You can't just have a little 16-bit controller that's running your refrigerator at home. It actually needs to be quite a beefy processor that's running these computations to be able to perform the AI algorithm with a lot of accuracy. And the more accurate the algorithm, the many more layers that it has. It's not uncommon to have neural networks that have hundreds of layers of neurons. And if you imagine like a 200 by 200 pixel image, that's 40,000 inputs that you need. Each pixel gets its own input into the neural network. So these are really, really big neural networks with a lot of compute performance required. Trillions of operations per second required from these neural networks. You also require low latency. Of course, if you're going to, let's say, fly a drone and it's going to detect an issue and you're going to have to do some computation and send the data back in real time, you have to do all that computation in real time, or you're going to end up accumulating data, and then you have to do something with the data. So multispectral cameras that are very expensive and that are sitting on farms, an alternative is to actually have smaller multispectral cameras flying around so you can detect where the crops are being damaged, or you can detect various things going on where the rotten tomatoes are in the field. But you have to do something with that data. You can't just accumulate it on the drone. You have to be able to compute really quickly and have very low latency. You also need power efficiency. Power efficiency, power is an interesting thing because it generates heat. So in order to build a box that has a lot of performance, you have to make sure that you're using very good power efficient silicon, or else it'll generate too much heat. It also means more cost because then the boards carrying the silicon will have to be further apart. And so you have larger boxes because there's more heat. So power efficiency is really key. But you also have to be able to compute quite a lot. So these are basically trade-offs that we're looking at. And then the other thing is privacy, keeping the data on premise. If you imagine an edge computing device that's able to track people coming in and out of a store, a convenience store, and track what people are buying, and it's a staffless convenience store, you wouldn't necessarily want to walk into the store if you knew that the camera was sending your data into a data center. But you might walk into the store knowing that maybe your privacy is pretty good because the data is being computed in real time and your data is not even being stored. It's just being used to accumulate some statistics of where you're moving around in the store, where the hotspots are for customers, or how many people are coming in and out. But to the extent that you can keep the data on-premise in an on-premise server, you don't necessarily need to be communicating over the network sensitive data like tracking people and things like that. And so what is the chip innovation required to meet those needs and those very strict requirements? This is where the action is. And this is why I titled this talk, The Edge is Where the Action is. Because the edge requirements for doing this heavy compute in low latency with low power is actually causing us to have to build chips that are very, very efficient, moving data around and having very efficient data flow on the chip. We also have to build better algorithm processing. We need to be using memory more efficiently because memory isn't free, even if they're very small chips. And the silicon process technology is still an issue. So Gordon Moore's law of trying to improve the size of the transistor in order to get more speed from a chip is still, there's tons and tons of investment in that kind of problem. So there's still a lot of challenges in the chip industry in order to meet the need for this insatiable desire to deploy AI algorithms everywhere, because of course there's a cost to being able to deploy such complex algorithms to get very high accuracy. And so how exciting is AI today? I thought I would explain by transporting you to August 2019 to the Hot Chips conference, which was over in Memad. And it was a very exciting conference. But this year was an interesting turning point for the Hot Chips conference. When I attended, it ended up that there was a number of new deep learning chips being announced. And if you looked at the last few years, AI was becoming kind of an interesting thing. There were some companies starting to dabble with AI and announce new chips in AI, but not like this August when there were this many inference chips being announced. Intel, Habana, Huawei, NVIDIA, and Tesla. And there were just about as many training chips being announced as well. So there were something like 10 or 11 or 9 AI disclosures all happening at the same conference, which made it practically an AI chip conference, even though still we had the big CPUs and GPUs and other kinds of devices. So, and there's a mix of startups and large companies, a lot of innovation going on in AI. I thought it would be interesting to show you, and you can go to the hotchips.org website and review these papers, and you can even watch on YouTube. They have links to the presentations. So let me give you some examples of real things going on, because I'm now going to switch to the Asia topic in my talk today, of things going on here and in Asia. First, AI dev kits have become available recently. This is an example of Intel-based dev kits, but just the idea of a development kit being sold as opposed to just use the computer that you're already using shows that people aren't satisfied with just your laptop or desktop PC. You want something faster. You want something more efficient. So if you're going to train a neural network, your laptop may not be fast enough, but if you go buy one of these Accelerator cards inside of one of these Intel mini PCs, then you'll be able to work on your prototyping of AI algorithms in a much more efficient way. Also, some companies are putting together like this development kit called the Neural Compute Stick that we developed, and putting it with a little Atomic Pi card PC. So this is just an example of what we're doing at Intel. But it's interesting to look in Asia at different kinds of development kits and AI technologies that are coming to market now. A very recent one that has already been made public is the AI development kit called Vision Seed by Tencent. Maybe many of you are familiar with this company from China. Even though it's kind of a cloud services company, and applications company, having a dev kit with multiple sensors and an AI accelerator on board. It's the Intel Accelerator, so I've been involved in this project. But it's really interesting to see such a small AI accelerator card that anybody, any developer can go get and start to develop with, create a robot, create a drone that has computer vision and AI. And they're not alone. There are many companies now developing these kits to be able to get developers, maybe even in colleges and graduate schools, to start learning how to program on their platform. Another example, there are many more examples I was going to talk about. At Intel, we have an ecosystem of developers. We're pretty much with open arms taking in, building relationships with a lot of developers. Many of these are in Asia. A number of them are either hardware developers in countries like Taiwan, in Japan, in Korea, in other parts in India. And these partners are either creating software so that they can run on various kinds of development platforms, very specialized AI algorithms. We'll talk a little bit about the kinds of AI algorithms people are developing, as well as hardware cards and boards that are based on various kinds of chip technologies. So, and some of them are integrators, integrating the hardware technology. And so there's a whole big ecosystem or channel where an end customer, like a fast food restaurant, would go to a system integrator. The system integrator would know which kinds of hardware technologies to be and software technologies to be using. And so there's a big chain of developers that are starting with some silicon, starting with some software tools, and then developing hardware boards that go into industrial PCs or servers like this one, and then ultimately get set into the end customer's business to help out. So this is our channel partner ecosystem in the IoT group at Intel that I'm showing. I'll focus on one of them in a second, but let me just share with you another example. A couple of companies in Taiwan that are developing PCIe cards, and it sounds very simplistic. Like, of course, you would take a chip and you would develop a PCIe card with it, but when an end customer or a systems integrator wants to be building these AI systems for the customers, they have to come get their hardware somewhere. And different hardware has different features. Some of them are built to the PCIe specifications, so they can be put like in this PC, this industrial PC that I was showing before. And some of them are smaller cards, so they can go into much more smaller places, like into a camera to make a camera. So whether it's an industrial PC or industrial edge computing server or a camera, there's different kinds of hardware developers that are in the ecosystem in Asia that are kind of tackling this kind of problem, is getting a piece of the AI business by building cards and building and supporting the customers. So I was going to show you a video of this exact, it's not going to have the sound, but it's this server actually running a partner's software. They're called Gorilla. And this box itself is from a company called IEI. So IEI builds the box and builds the boards that have the Intel chips on one of the cards. And then the Gorilla software is actually running 16 cameras worth of AI. So 16 cameras are connecting into the box. And where you see me demonstrating this on the table, it's this exact box here. And the data is coming out of memory instead of streaming from a camera, a real camera. But you can have car license plate detection, car traffic detection, looking at which cars and then classifying the cars and looking at what, determining what model of car they are. And so there's a lot of car and traffic related AI algorithms that could be running. We run on an average 2 or so of these AI models, algorithms on each chip, and there are 8 chips on the board. So there's 16 channels of AI algorithms running in the device. And then people are being tracked, and so it's for public safety and traffic. And it's this kind of software could go in a small, like a compute facility that's near the side of the road. So the cameras that are near the road or over the road don't necessarily have to send video all the way into the data center. It can go through a 5G connection right to a local compute facility with a small number of these servers. And then you're getting that local area's worth of metadata that you can then share with other parts of the city. And then you can kind of imagine that in the next few years, those kinds of systems would allow for better traffic congestion, dealing with the traffic congestion. Warning your automated, once cars, more autonomous cars are on the road, then it becomes a bit of an autonomous system. But we'll see. Right now, researchers are writing papers about these kinds of systems, and they're just starting to be deployed along with the 5G infrastructure. So that was one example. And so now I'll talk about sort of the, what are we doing and what are the devices that you'll actually see in some of these systems, moving from the edge devices to the edge servers into the cloud. This really gives a summary of the Intel product line. And what I'm showing here is, on the left, what the edge devices are using, these MoviDus chips. This came from the startup I was working for. And we've been now developing new generations of these chips. And the important thing about the edge devices, especially ones that are going in the cameras, that you get a lot of performance and you have very low power. So the absolute performance comparison against a data center chip, there's not a very good comparison at all. But if you look at the performance per watt of power or the performance per watt of power per dollar of cost, that's where these things really shine. Because you have a very limited amount of power, you couldn't put a data center processor from over here into a camera. It wouldn't work. Because of just the sheer wattage required from the data center processors. So then you have these edge servers like this one here and larger edge servers depending on if it's hundreds of cameras at an airport wing, then you need a larger server than this one. This would only take about 8 or 16 cameras. And then you would use these Intel processors that are very similar to the ones in your laptop, but you put them on a card and then you add to it some acceleration, like either from the MoviDus chip or from an FPGA. And then you can get a lot more AI performance out of your small edge server or your gateway. There's a new class of product called an AI box or AI appliance, where you basically already have an infrastructure for a server, or you have an NVR that's basically collecting data from cameras. Now you want to just connect up to a smart, intelligent device that can then do analytics on 32 channels or 64 channels of video. And these kinds of AI appliances are now being built by many different companies. We find the most aggressive ones are in Asia, coming to market very quickly with small boxes that have quite a lot of AI performance in them. And then, of course, in the data center, you also want to be running AI. In many cases, you're detecting or cropping an image, but then sending it for classification into the cloud. So the classification engines that could be running in the data center could be quite sophisticated. If you think about a supermarket, how many products are on the shelf at a supermarket? How many different labels have to be analyzed if you want any label of any product to be recognized by a classification engine? That's the kind of algorithm that you would run in the data center. But to detect the person and to detect when the person is grabbing the product and putting it in their cart, that's something that you can do at the edge. So you would have AI algorithms running in the edge, another AI algorithm running in the data center to be able to do a staffless store. So it's not always whether you're in the edge or in the data center. You usually need to be partitioning algorithms among the different resources, putting the appropriate very heavy algorithms in the data center that need to do the classification, the very appropriate edge algorithms that are doing the detection and a little bit lighter in terms of performance. So I will explain now how the MoviDus chip works. I recently was able to do a video, and I was really excited to do this video because it's really hard to actually explain without using a lot of CG how the chip works. So I thought I would just spend a minute. Maybe I should fast forward to the middle of the video because you're not hearing. Can I fast forward? Uh-oh. Maybe I can't fast forward. But anyway, the idea of the MoviDus silicon is that you have a lot of performance and very low power. So roughly 3 or 4 trillion operations per second in about a watt or 2 of power. And the way that you get there is by minimizing the data movement on the chip. So it would seem like the more compute you have, the more power it would consume. But the power is mostly consumed by getting data in and out of memory and moving data around on the chip. So the team, when they founded the company, they thought there's probably a lot of room we have to lower the power if we can only figure out better ways to move data around. So in a traditional chip, where you're licensing IP and you have CPUs and GPUs and DSPs that are integrated onto the chip, they usually have data buffers, and the data is moving around from these data buffers. That causes some power to be dissipated. But on the MoviDus architecture, we actually have a scratchpad memory that everything is connected to. So because this is multi-ported, you can get CPUs, DSPs, and other accelerators to be moving data around minimally because the data is really sitting in place in this scratchpad memory. So as your algorithm and as your application algorithm kernels are running, you can manage where the data is coming from and where it's going to. And as long as you're managing that appropriately, you're minimizing how much data movement actually has to happen. And then you can take a bunch of these chips and you can put them on boards. The other trick to building these chips is that you have to have kind of a heterogeneous set of resources because computer vision and AI requires not just the deep learning to happen, but people may have customized algorithm they need to run on general purpose processors. So we have DSPs that were optimized for computer vision, as well as some engines that were optimized to run hardwired algorithms. So they're very efficient. And one engine in particular that was built from the ground up to run neural networks. So it can run several different neural networks, which you would want to run from some video sources. And you would want to run those neural networks at the same time you're running computer vision and everything else on the chip. So the fact that the chip has a lot of parallel compute capability and that it's trying to lower power makes it a pretty efficient engine. And then if you put 8 chips onto a board and you put several boards into an edge computing PC, it's quite a powerful PC that could have many of these chips running tens or hundreds of trillions of operations per second. And then we wrap up this software that I'll talk about a little bit more. But that's basically what the MoviDus chip is doing. Now let's shift back to some interesting companies in Asia. So I was trying to think, how can I not have some examples from other parts of Asia, Japan? So this company, LeapMind, is very interesting. They're able to make convolutional neural networks or deep neural networks a lot more compact. And that's very tricky. How can you remove a lot of computation from an algorithm and still get the same results or still get the same accuracy? Well, they've created some research and patents, and they're able, through some tricks, to be able to get compressed algorithms running on smaller engines, maybe even in an ARM or a small CPU on a cell phone. That would
Gary,
be able, I'm sorry.
Let me interrupt you and say that our speaker on November 14 is from LeapMind.
Oh, LeapMind.
Yeah.
Yeah, fantastic. So this is a good example. You'll hear more about it if you come to that event. Thanks, Professor Dasher. A company that I worked for based in Tokyo, Morpho Inc., has combined a lot of photography and imaging capabilities with deep learning to be able to do much better imaging quality on lower performance processors like in a cell phone. So they started out by being able to do various kinds of image and video stabilization on a cell phone using advanced software algorithms. And now they're doing a lot of AI and implementing computational photography using AI. and they won an award at the recent Embedded Vision Summit for Product of the Year. So I finally, the last few minutes of my talk, I wanted to talk about trends that I'm seeing moving forward. I think from the vantage point of a big company building silicon, we're supplying in a lot of markets, we're supplying in a lot of different regions of the world, and there are some trends I'd like to point out. These aren't necessarily market trends, but certainly chips are really worth nothing unless the software works. So the software is actually the critical piece in getting silicon deployed in efficient ways that various businesses can take advantage. So when you think about the software journey that people are taking in order to implement, whether it's AI or whether it's just about any application, you need to explore and do research, and you need to prototype. You need to optimize your code for the platform that you plan to run it on, and then you deploy the algorithm. And so what I'm seeing is a trend among a lot of different companies to have more and more efficient tools so that developers can get from exploring to prototyping to optimizing and deploying really, really quickly. And it's not like we're trying to cut corners. We're actually trying to give more power to the developer. And at Intel, we have a tool suite that was announced a year ago called OpenVINO that is able to take people's neural networks, algorithms, and then port them to any architecture that we have at Intel. And other companies as well are working on specialized tools that will be able to allow you to prototype and get to market very quickly. And I think that's very interesting, and it also goes hand in hand with all the developer kits that different companies are coming out with to make it really easy. And the byproduct of that means that if you're at a university or you're a graduate student and you don't just want to use your desktop to run all of your experiments, you can quickly get different tools and compare and contrast performance across different architectures, or you can compare and contrast your algorithms running in different environments. And usually these tools are getting easier and easier to use. And the very macro trend that I'm seeing, if you look at when I was a child and I was at the high school programming on a machine that was connected up to a mainframe, and then you look at how people were migrating more to their desktops and now to mobile devices and doing a lot of application developments in mobile devices. There's also a trend that people are now, as you probably all know, connecting to the cloud and using cloud-based tools to implement your algorithms. So you don't have to have the machine on your desk anymore. You could be connecting up using various kinds of services and any kind of cloud service. And there are tools that let you arrange your algorithm, implement them. Companies like Google are offering environments to run AI and to develop AI using their cloud software. And there's also hardware accelerator FPGAs, AI accelerators. And these boards you have access to because you have access to the cloud. And in their data center, they have a lot of these accelerators plugged in so that you have access to all of this hardware without even leaving your PC at home or at school. So the way in which people are developing algorithms I see is evolving, basically making it easier on the developer, easier to access developer tools, easier to access them over the cloud, to implement them. But of course, at the end of the day, if you want to build cameras that are going to be installed in a fast food restaurant, you really need to develop the hardware. But the development journey is being made much, much more efficient. Another trend I wanted to point out that we at Intel called workload consolidation is a trend that we've seen over several years, and I think it's going to continue more and more in industries like industrial automation, where it used to be you would have, let's say, a PC, you would have a camera, like robots, and then data, the robot would move things around, the camera would capture information, send it to the PC, it would then go over to another server. Now we find that all of that functionality is getting into one board in one PC, or connected to the cameras. And in some cases, robots themselves are being developed with the camera in the robotic arm and the compute inside the robotic arm. So you really just need the robotic arm to move around and look and count the number of things going by, or detect various product defects and those kinds of things. So consolidating these workloads that used to take a lot of different resources across a whole company can be put into like some small or medium-sized servers and have the consolidation of all of these different kinds of workloads. I think in different industries, this will be interesting to see how it evolves. And I think it's also an example of how we're building our silicon to be able to support multiple workloads, some general purpose, some working on pixel data, some doing computer vision, some doing audio. So we have all of these different resources that we're building into the same silicon. So I hope that gave you a really good sense of why this AI thing is very interesting and important, and why now, how we're making use of it in the industry for edge computing, and also what are some of the different kinds of devices that we see here and in Asia. And I look forward to doing much more where I've traveled to Asia quite a lot. It's an exciting place. It's very dynamic. I think there's definitely in the US and in Europe and in Asia a lot of interest in AI. But for some reason, the AI technology is really taking off in Asia in a variety of different ways that maybe we're not seeing in the Western society. But anyway, that's my talk. Happy to answer your questions.
So Gary, let me ask the first question. So as somebody who's in the chip industry, do you see a difference in mood in the chip industry? You pointed out the Hot Chips conference and how much of the Hot Chips conference was AI. Would you say that this is really breathing new life into the industry?
Well, I do, yeah, it's breathing new life because I think there was a period of time where startups weren't really getting funded. And then now, because of deep learning and computer vision and AI, it's breathing new life into a lot of startups that were working on AI. Now, when I talk to some of the investors that are walking around at Hot Chips show, they were saying, well, we don't really know who the winners and losers are. So that's the bad news, is it's really hard to tell. Is one startup that builds a chip that's the size of the wafer going to win or lose? It's really hard to tell, but it's very intriguing. A company did actually build a chip that's this big, one chip per wafer. And how do you package it? How do you cool it? They're basically breaking the rules in the industry and inventing something new. That was Cerebras. So there's a lot of companies that are getting funded, and so I think there's kind of an interesting renaissance going on in algorithms that can do AI better. And to me, it's still trudging along at a pace.
Yeah.
But the fact that a lot of new companies are innovating, and it's not just the big companies. There's a lot of different companies.
Are you interfacing with different kinds of people when you're talking about Intel products and so forth? Are you talking to a different range of kind of industries, or do you see any changes there?
I think
they've always been there, I guess.
The number of kind of roles people take on when it comes to edge computing, you have data scientists. And the data scientists are just trying to figure out, what data should we be analyzing? How do you train a neural network? You can't ask that question until you actually have the data you need. And so sometimes, you have to have a whole group of data scientists that help feed the right data to the engineers who are actually training the deep learning algorithms. So I think we're seeing a different cross-section of engineers that it takes to come up with the right algorithms in order to have something like automatic pedestrian detection. I mean, think about it. I think it was, I don't know exactly which car company it was, but when the first pedestrian detection brake system came out, I mean, it really was something, because the driver is supposed to be seeing the pedestrians all the time, but in that one little case where you might be missing it, the LiDARs and radars and vision sensors may not. And so it's very interesting that the development of these algorithms now means there are a lot of different kinds of computer scientists and engineers and electronics engineers required. So I think I'm seeing a different kind of cross-section of people required to deploy this kind of technology.
Okay.
And it's different than just having one camera company using silicon that's been around for a long time and then an installer that installs it. Now there's a much larger ecosystem, different companies getting involved, some building software, hardware, cards, chips. So many more moving parts, I think.
So now we get into the uncomfortable stuff. So the computer chip world has been very international, world sales. And I think Qualcomm was selling $15 billion of chips to China, for instance. With all the things happening the last few years, are you seeing decoupling? Are you really seeing, is the company kind of, maybe not so much talking about the direction of the company or so forth, because that's probably sensitive, but personally, are you seeing a different kind of mood?
Well, I'd like to think, and I think I've observed that in technology, people, no matter where, no matter what country you're talking to people in, we all have the same goal. We want to build better technology to improve people's lives. So I think there is a bit of a different mood when maybe politics and governments kind of get involved. But I think still there's some hope that, well, we're all just engineers. We're just living in different places, and we want to get along and kind of make technology better. And I see that. And so it was interesting to see at the Hot Chips conference, there was one company that actually couldn't get visas to attend the conference. They were one of the keynotes. And so they gave the keynote via Skype. So technology solved the problem. And I commended them for pushing past that problem to be able to show up at an international conference so that people could hear their talk. So I think engineers are engineers.
You'll find it. You'll innovate a way around it somehow, huh? Okay. Go ahead.
To the extent of Dr. Dash's point, obviously there were two NLAI companies 2 days ago that were sanctioned as part of this trade dispute. You probably saw in the news. And it's now affecting their startup ability, and obviously they're both in PRC, and it's part of the machine learning mostly for surveillance technology. So to extend on his question, is that part of the reason why in Asia things are much more advanced? Because in Europe and the United States there is a political and cultural history that maybe is dissuading some of that advancement that we, like for example, license plate recognition in Los Altos Hills and Los Altos. There's been a lot of controversy about, we know we can deploy it, we know the sheriff wants to use it, but then people are saying we don't want to use it and we're the taxpayer, And
I think different
Shanghai
you're right.
would say that.
Different places have different senses of privacy, clearly. More advanced versus less advanced, there are developers all over the world that are advanced, so I wouldn't say one place is more advanced than the other. But how technology is used and deployed is very different from place to place, as you notice. So we live in exciting times, for sure, and I think that's about all I can say on that topic.
Okay. Go ahead.
Over here.
Yeah.
So you talked about, specific bespoke AI chips, right, for edge computing. Now, there was a talk about Qualcomm's selling $15 billion worth of smartphone, processor, the heterogeneous compute. It has CPUs, GPUs, DSP cores, all dedicated, right? And cost is a big factor, right, for edge computing. You can put a really expensive system out there. Why not tap into this wonderful economy of scale that the smartphone chips have, and use that to repurpose it for edge computed purposes? Why do you need an expensive? For inferring, it's okay. If you're going to train, I agree. You need a more dedicated resource. Why not? You would tap into this economy of scale. It's very affordable.
That's an interesting question. So mobile phone processors are very commonplace. I wouldn't say they're inexpensive, though. So if you look at the cost of a mobile phone processor, it's not so inexpensive. Actually, people are looking for less expensive silicon that can do just as much as a mobile phone processor, which is why there are all of these other kind of purpose-built custom chips that are dedicated to AI, let's say. When AI has to be just one of many functions on a cell phone, it has to unlock, given your face, but it also has to be running apps and games and other things. So I think mobile phone chip companies, you'll see, are also playing in this game of designing chips for AI, dedicated to various kinds of other applications for edge computing. But it's not just a one-to-one, like we can take chips from a mobile phone and they're immediately usable in a camera. There's some conversion, and in fact, some of them are expensive. So,
The thing is, end of the day, if you don't have volume, it's going to affect your economics.
That's true.
Right? So you already have this great economy of scale, right? Billions of processors that are already being manufactured. Why not tap into it?
Yeah, I think it just depends on what tapping into it really means. Those companies are also building silicon for other things as well. But the mobile phone has to have mobile communication, and there's special features for the mobile phone that maybe other kinds of computing needs don't have. So that's why there's some customization required.
What does the device cost? That may answer his question.
Like this kind of industrial PC server, I can't say, it's not our product, but it's inexpensive. I mean, you could buy, I mean, if you wanted to run your own software as a service over a cloud and you wanted to develop your own cloud, you'd be buying much more expensive servers. So to do enough that you need to do on-premise, if you run your own convenience store, this is good enough and this is inexpensive enough. So you don't have to be investing in lots of high performance data center grade kinds of computers.
How much of an acceleration can somebody get by using, say, one of your system board with the MoviDus processors on it, in what, a drone or something?
That's an interesting question. So a lot of customers will ask, I have an algorithm, how much will it accelerate if I use your silicon?
Yeah.
Yeah, we have so many different examples of customers that have run on some basic CPU, and then they use our accelerator and they get 100x or 183x or 300x. So it just depends on how efficient it was to begin with, and then where you currently are, what your algorithm is, what platform you're using.
Okay.
Yeah, there's a lot of variables in that, so it's hard to give one answer.
Okay, go ahead.
So I have a question. So since Intel, they say that they have a great silicon photonics in Intel, so what do you think the role, future in silicon photonics in these AI chips, such as silicon photonics-based AI chips, as well as also talking about the chip on board optical interconnection with COBA, important. So if that's a COBA, which is based silicon photonics, you have a huge, big ecosystem. So what do you think the vision in silicon photonics in this edge computing?
Two things. I don't work in that group, but I should say in the industry there are a lot of interesting experiments being done on how can we speed up computing, lower the power of computing. As you say, silicon photonics, there's also neuromorphic computing, a lot of different kinds of ways of implementing these algorithms. How promising they are, no one has a crystal ball, but it's really interesting to see that a lot of these projects are getting funded, and we'll see how far they go. I can't tell you. Sorry about that.
Go ahead.
Gary, at the very end of your talk, one of the final points that you made was the difference potentially in Asia and the US. One of the things that I noticed is I listened to a talk on PBS on deep learning. And one of the biggest difficulties they talked about was recognizing cats. The difficulty in doing something which sounds very simple. Then I'll watch the PBS NewsHour running a series on China, and we'll find out how successful facial recognition is being applied to social credit. For instance, in detecting people who are jaywalking and immediately putting their faces up and for public shaming, etc. So is there a disconnect between the US and Asia in terms of the capabilities there? Maybe one other question, a follow-on to the last gentleman's. It sounds like the innovations, because we're pretty much at the end of Moore's Law for silicon, it sounds like most of the innovation is in what, massive parallel processing in order to...
Okay, one question at a time. So is there a disconnect when you're watching cats on PBS being recognized by, well, I think it's an educational program, and so they're going to give you a simple example. There's a famous example of a bunch of blueberry muffins and a bunch of dogs. The dogs kind of look like the blueberry muffins, and so can the AI algorithm, or can you as a human, detect the difference between is it a muffin or is it a dog? These are used for educational purposes. I actually don't think that, is there a disconnect between the way Asia is deploying better facial recognition to detect people jaywalking on the street, but on PBS? No, I think it's just the way the technology is used. You'll see a lot more traffic cameras and a lot more jaywalking cameras, because that country, the way the culture is, they'd like to do that. And maybe Los Altos doesn't want to do that. So we have various ways of deciding, do we want to deploy the technology or not? And maybe it's just a decision of how to deploy the technology. But it's the same technology. The question is, how much do we want to deploy it for everyday use on every street corner here versus in a different city in a different country? And then you also asked about the second question.
Silicon.
Oh, the silicon, yeah, no, that's a really good point. So I don't agree that it's the end of Moore's Law. I think there's still a lot of innovation going on at transistor level, the physical technology itself, to be able to gain some efficiency and speed up. But there's also a large amount of work being done in architecture and how you organize the transistors. So I think there's bigger gains to be had these days in the silicon architectures. And you'll find different chips. MoviDus, for example, came up with a different kind of way to develop the chip. And that's how we were able to get a good efficiency. So there's new kinds of technologies. Some of the AI startups, for example, are putting memory close to the compute engines. And they have a lot of local memories being put near the compute engines. More expensive, maybe a little bit different kind of architecture. But different kinds of architectures are going to get much, much more gains. Not just the silicon technology. But I think there's still room for growth in both areas.
Let's do stacking.
Yes. All right, other questions?
Yeah, go ahead.
Yeah, so this is a very nice topic. So in case of the process technology you mentioned in the slide, do you think about the VPU versus the CPU, is there any fundamental difference so that process people can contribute to?
So are you asking about the fundamental differences between CPUs and the VPU that we developed? Oh, in the case of process technology, no. The same process technology is being used. It's the architecture that's very different. CPUs, even GPUs, have to be fairly general purpose. The VPUs were designed specifically for computer vision. So they're kind of purpose-built for computer vision.
So one of the things you mentioned, one of the trends you mentioned at the end of your talk was workload consolidation, putting different functions into one device instead of multiple devices. Is that basically because of the time it takes to communicate across device boundaries, or what's driving that?
I think it's because of the total cost of ownership.
Okay.
But also different protocols are being used. It's easier to have the data within a chip or within a board or within a PC. But yeah, it's a combination of maybe efficiency and cost and speed and accuracy. I mean, all of these different things that weigh into the requirements overall for edge computing. But yeah, I don't think there's just one driver of that.
Okay. Other questions? Go ahead.
Could you comment on regional variations within Asia on use cases for products and technology that you sell?
Regional use cases.
So is Japan any
It's hard to say there are specific, like this region focuses on some. Traffic cameras is an interesting example in China because there's just a prevalence of traffic cameras. Japan has a big industry of factory automation, FA, and robotics. And so I think I've seen use cases. Some of them we're going to see at the Olympics, which is really interesting. Some of the big sponsors of the Olympics coming up in Tokyo may demonstrate various kinds of interesting technology in robotics and automation. In Taiwan, we see a lot of the board design and ODMs and kind of the companies that are in the middle of the channel. We're building the silicon and other companies building the silicon, supplying them to build the machines that are then getting integrated into the end customer. So not as many end customers, not as many silicon companies, but definitely a lot of the people in companies that are in the middle of the channel. In Korea, in India, there are a lot of companies that, I don't know why, it seems that the number of companies that I know build the dev kits, there are a number of them in India who do that very well. And then they'll label them as a TI dev kit or an Intel dev kit. And so taking the software smarts, I think, that has been built up over the years, I mean, I would say in India, there's a lot of companies that have very large software teams. Enables maybe better use of using the silicon to build dev kits and development platforms. But I don't know if that's a regional specialty because there are other dev kits coming from elsewhere as well. But yeah, that's a hard question to answer because I don't think it's regional. I think wherever there's a density of engineers, there's going to be a lot of interesting new AI technology.
The Asian population, there is a huge investment in robotics to assist.
That's right, to assist the elderly. So yeah, maybe that's one of the factors that contributes to the robotics in Japan.
So I'm going to go back to this decoupling once. I'm seeing news articles that the result of putting companies on the entity list so that the U.S. companies can't do business with them is basically going to encourage Chinese companies to ramp up their chip development activities and have lots of new competitors.
Maybe, although I've seen that everywhere there's ramping up of chip design capability. So there are chip developers all over the world. I would say since more startups are getting funded, I know of some AI startups from Canada now that I didn't know of just a year ago, various different regions. So I would say maybe you're right, but maybe there's just also many chip companies popping up everywhere. So it's hard to tell. But,
Good.
Yeah, I don't know.
That's a legitimate perspective. Thank you.
Yeah, I was just reading online that your products are made using TSMC process.
Products are made using the TSMC process.
Yeah, TSMC is one of the fabs that are used to, a very big one that's used to fabricate chips, and many people use TSMC. There are others as well, but yeah, that's one of them.
Intel Silicon and TSMC.
Intel has its own fabs as well, but yeah, TSMC is another alternative. Question in the back?
It sounds like the overarching role in AI is improving people's lives. I'm trying to just sum that up. And I'm wondering, based on even like the Hot Chips conference, how the companies are actually measuring that like goal, like what exactly does that mean? I mean, it's pretty broad, so I don't know if you can speak to that.
Yeah, I think so the question is, if AI is meant to really improve people's lives, then what do chip companies like the ones at Hot Chips, what are we doing, or what can we do, or how do we measure how effective we are at improving people's lives? I think, well, one thing to say is, depending on the size of the company, like a small startup is really trying to get something done to get some software running and demonstrate something that's efficient or high performance or low cost. But larger companies like Intel and other large companies have the reach to be able to communicate with end customers and communicate with the channel and learn from what end customers are trying to do. So we have analysts and marketing people talking with a lot of the end customers. So we're trying to find out, what is their aim? They're the ones that know ultimately what they're trying to do to improve either the cost of running a business or building robotics for the elderly, or here's a really good case. So National Geographic, in fact, I kept on telling myself I really should talk about this example, so I'm glad you brought it up. There are other examples of this same technology, but as just one example, there was a company that wanted to build a camera and put the cameras into the sub-Saharan desert to be able to detect a poacher before the poacher kills the animal. Now, the current technology is that you detect the sound of the gun. So when the sound of the gun is detected, the authorities can be alerted as to where that sound came from. But then it's too late. The animal's dead. So the idea is, using computer vision technology, you can build these cameras, and National Geographic and the Leonardo DiCaprio Foundation have funded this company, Resolve, to build these cameras. They're using our Intel Movidius Chip, and it's been publicized at CES. We showed a demonstration. We built like a little forest. And essentially, it's a really serious matter, because you could be saving tens or hundreds of thousands of animals' lives when you detect the motion, and then you decide with your neural network, is it an animal moving or is it a human? And if it's a human, then you send the data to the authorities. If it's an animal, you just shut the camera back off. So these cameras have a battery length that's quite long, on the order of years, and they can be stuck in places where you wouldn't see them, but when the poachers are walking by, they're detected, and then the rangers that have to cover a very, very large amount of space. So it's a story that's sort of gone viral in a way, and there are other countries that are doing similar things. I think in China, they're trying to protect the Bengal tigers, and there are technology companies that are building these kind of cameras. But to me, this is definitely one of the ways in which AI is being used for good. But there's a chain of, the problem is known locally, and then they come to the camera company. The camera company says, yeah, maybe we can solve the problem, and then they come to the device company. And so the device company is really just hearing from our customers, what do they want to do and why, and what do we feel we need to support. So there's a lot of good, interesting technology that's being used for good. It's just a matter of taking the time to support these companies to build the cameras and get them deployed. So it's an interesting story, and I think PBS even did a special on that particular company.
Actually, I see several hands. Back in the back, you
Good question.
first. Yeah, you.
You mentioned that chips can do trillions of calculations. I assume that's a couple teraflops then. So what sort of wattage, like performance per watt, do you know?
You know, that kind of question is exactly what would lead you to go compare and contrast several different, so go buy the data sheets for 10 different chips and you can measure it yourself. There's no one answer. Different chips running different workloads will have different amount of performance at different amounts of power. So, but that's the kind of spec people want to know. And so it depends on a lot of different things. How your neural network was trained, how it's running, what neural network is running, what exactly is it accomplishing, how many inferences per second, and then how many, what's the power that's being consumed, or even power is sometimes the wrong question. You want to look at the overall energy to complete a complete job as opposed to the power at any moment, which could be fluctuating. So there's no one answer. But it is the right question. There's just no one answer.
To use an example, you mentioned the human detection algorithm. Have you tried that on your MoviDus chips? Getting better than human detection rate?
Yeah. So in about a watt or so of power, it can run at typically a couple of trillions of operations per second. Something like there's typical benchmark neural networks that will do this kind of a job. Whether it's AlexNet, which is fairly simple and a little bit older, or something more recent like GoogleNet, or the most recent benchmark that everyone seems to be using is called ResNet 50. ResNet 50 is a fairly sophisticated algorithm that can do tracking of objects or faces or people fairly efficiently. So yeah, it also depends on like what has it been trained on, or how you're running it, and what's the data. Whether you're running it in 4-bit mode, or 8-bit, or 16-bit, or 32-bit, or floating point 16, floating point 32. So there's a lot of different variables and knobs and switches to how you're running the algorithm.
Let's quickly go. A couple of questions back in the back over here. Yeah, back in the very back.
Just wondering what are some promising edge computing and AI startups you've seen or heard about that are coming from Korea?
Wow. So there's a Korean consortium that has a Bay Area office. Am I thinking of Kotra?
Yeah.
Yes. If you go visit Kotra and just walk through the hall, you'll have many, many, many different companies. I'm not going to name any individual ones because then the others will come back to me and say, that's unfair. Why did you mention theirs and not mine? But I would say groups like Kotra are facilitating companies from Korea to be coming to the Bay Area and establishing their presence here and working with other companies. So I would say that's a good place to start. Look at the Kotra website.
Go.
Is there a home market for these edge boxes, like either for students or hobbyists, like analogous to like Raspberry Pi or Arduino, or for people who might want to run their own agents as opposed to like Google's or Amazon's in their home for privacy purposes?
Yeah, after the seminar, I can tell you about a few companies you can go contact if you want to get some of these small industrial PCs, but you could also build them yourself.
Before we close up, Gary, you had something you wanted to say to students here.
Oh, yeah. In the marketing group that I work in, we might be hiring, coming to the end of the year, an intern for next spring. So if you're interested in engineering and you're very technically minded, but also interested in marketing or sales or business, that's a really great combination. If you're interested in interning in our team, please contact me. I have my business cards. Thank you.
And we have some refreshments afterward where you can initiate this kind of conversation. Any rate, thank you very much for bringing this down to the level of the chip, which is really, this whole move toward edge computing is causing changes all the way up and down the technology stack. And Gary, really appreciate you coming and giving us good presentation.
Real pleasure to come speak here. Thanks again. Thank you.